Okay, so the next example we're going to be working through is trying to figure out some of the forces developed in this truss here. So in particular, we are worried about the forces in CD and JK. So in this instance, since we're only worried about the forces in a couple components, we're going to use the method of sections to solve this. So what we're going to do is we're going to be taking a slice, we're going to be slicing it along this line here. So when we do that, essentially what we're doing is we go ahead and we treat whatever is left as a rigid body, and then replace any of the members that had been cut with just forces along their axes, and then apply the equilibrium conditions to the cut section that's left behind. So I'll just move over here. So again, just reproduced our diagram here up at the top. Got our loads, got our reactions, so on and so forth. And then again, we're cutting along this line. We're cutting along this line instead of, say, this line. Either would work, but if we cut along this line, then we kind of have to deal with the kind of what's left behind for the angled. Basically we have to deal with the angles of these forces GD and GK, which might be annoying. Whereas if we cut along this section here, then basically we're left the forces that are left behind as a result of that CG and GJ are vertical only, so it kind of simplifies our analysis a little bit. So doing that, essentially what we do here is we go ahead and I'll zoom in a little bit. I draw the remaining structure. So again, we've got the structure that's left behind. I shaded it in a bit here to kind of give you the idea that yes, we're kind of treating the entire thing that's left behind as a rigid body. Because those portions, this frame made out of these members pinned together would be a rigid body in and of itself. That's a rigid frame. So we can apply forces to it and so on and so forth, and we can still expect it to hold its shape. So got our free body diagram. We got the external forces applied. We got the 3 kips each at the 3 locations. And then we've got the internal forces that are applied based upon the forces in CD, CG, JG, and JK. So the ones that we're worried about are CD and JK. So what I'm going to do there is I'm going to take a moment about point J. So about this point here. We've got a number of forces that are acting, that have their line of action that passes through J. So when we're doing this moment analysis, this 3 kip doesn't matter, FCG doesn't matter, FGJ doesn't matter, and FJK doesn't matter, because they're all passing through that point. So the only ones that affect things are these two 3-kip forces and FCD. So I'll just add those up. So the taken about this point, these two moments, these two forces here, they're both causing moments that are counterclockwise. So those will be positive moments. FCD, on the other hand, that'll be causing clockwise rotation. So that'll be a negative moment. So just add up those. So we got the 3 kips by 4.5 feet, plus the 3 kips by 9.5 feet, minus the 6 feet times the FCD. So again, 6 feet here, and then 4.5 feet from here to here, and then another 4.5 feet from here to here. So based upon that, relatively easy to solve for FCD. Got 13.5 kip feet plus 27 kip feet divided by 6 feet gives us 6.75 kip. So it's positive value, so that means that the initial assumption that FCD was under tension is correct. Tension. And then next thing to do, worried about our FJK. So let's take the sum of the forces in the x direction, FCD, and FJK added together. Obviously, when we solve for FJK, move FCD over to the other side, which means plug in that value, which gives us a negative 6.75 kip. So, yeah, there we go. That's a fairly quick and simple way to solve for those two values that we're looking for. And that is, yeah, that's about that. As I'm sure you could probably imagine, based upon watching the previous video example, especially when we're only trying to solve for one or two forces, this is a far less tedious way to go about it than using the method of joints. So, yeah, that's about that.